Maxwell showed that electromagnetic waves have linear momentum and so can exert pressure on an object when shining on it. Of course, the pressure is very small, or else you'd feel an impact from a bright light shining on you. Now, you're probably thinking that if something doesn't have any mass, it can't have momentum, because we all know the equation for momentum is P equals mv, mass times velocity. However, it turns out that since electromagnetic waves have energy, that has the same effect as if they had mass. In fact, Einstein later formalized this by saying that mass and energy are equivalent. So, a light wave carrying an amount of energy, delta U, to a surface in a time interval delta t, if it is all absorbed by that surface, will give it an amount of momentum that we'll call delta p. That is equal to the energy divided by the speed of light. Now, if the light reflects back off a surface, and so it is effectively bouncing back along its tracks, that light has had twice as big a change in momentum as if it got absorbed. In this case, the change in momentum at the surface is 2 times delta U over c. For all cases in between 100% reflection and 100% absorption, the gain in momentum will be somewhere in between these two values. Let's put that energy in terms of the intensity of the light. If we assume that our light has intensity I and hits a surface that has area A, then the energy delivered by that light is power times time, which is intensity times the area times time. And so the change in momentum is energy over c, which is I times A times delta t over c, if the light is completely absorbed. Now it's time to think back to mechanics. We remember that if there is a change in momentum, there must have been a force applied, and the impulse of that force, which for a constant force is F times delta t, is equal to the change in momentum. That's the impulse momentum equation you can see at the bottom. And from that we get that the size of the force applied by the light hitting the surface is delta P over delta T. And we know that delta P equals I times A times delta T over C. So, substituting in, and we can see that we can cancel out the delta T's, we end up with an expression for the force exerted by light hitting a surface. And that expression is, the force will be the intensity times the area over C if the light is completely absorbed, but will be double that if the light is completely reflected. If there's a force, we can find the pressure, which is just force per unit of area. So that just equals intensity over C for total absorption, or 2 times I over C for total reflection. For example, a typical amount of pressure from sunlight on Earth is about 6 by 10 to the minus 6 newtons per square metre, which is so small that we don't feel the impact when we step out into direct sunlight. One space propulsion method currently being studied is the use of a solar sail. The idea is that sunlight striking the sail will create a force that pushes the ship away from the sun. So a question for you, what kind of surface would you want on a solar sail?